Hi everyone, my name is Zimil and in this section I will introduce Microsoft two-phase immersion cooling deployment and walk through the key timeline milestone of the project. This will set the context for the rest of our presentation where my teammates will discuss the business driver, technical design, benefit and risk of this innovation. In April 2021, Microsoft became the first hyperscale cloud provider to deploy two-phase immersion cooling into live production environment, and its Azure data center in Quincy, Washington. This was not a laboratory experiment or a small pilot setup. Microsoft placed real production workloads into immersion cooled server. Services such as Teams and Outlook were routed through this infrastructure to test reliability under real operating conditions. The system works by submerging servers directly into dielectric liquid. This liquid has a boiling point of approximately 50 degrees Celsius or 122 degrees Fahrenheit. As a server operates and generates heat, the liquid absorbs the heat and begins to boil. The vapor rises, make contact with the condenser, cools down and return back to liquid in a closed loop cycle. This design represents a shift away from traditional air-based cooling system. Instead of pushing air across heat sinks and through server racks, the cooling medium makes contact with the hardware itself. This transition was significant because rack level power densities have steadily increased over the past decades. As processor performance increases and workload becomes more compute intensive, traditional air cooling systems become less effective at removing concentrated heat loads. Rather than continuing to incrementally improve air cooling, Microsoft explored an alternative approach that could support higher density compute environment more efficiently. Now that we understand what was implemented and why it was significant, let's look at how this project evolved over time. Okay, the first phase of this timeline begins where Microsoft's involvement. Prior to 2014, immersion cooling had already been used in high density cryptocurrency mining operation. This environment required continuous full load GPU performance, and immersion cooling proved effective at managing extreme heat load. This demonstrates that liquid immersion could operate reliably under sustained high intensity conditions. Between 2014 and 20, Microsoft conducted internal research and development on advanced cooling technologies. This include evaluating cool plate liquid cooling system as well as full immersion based design. During this period, Microsoft collaborated with industry partners such as Allied Control and Vivine to explore practical implementation at a data center. The key milestone occurred on April 6, 2021. On this date, Microsoft activated the first production two-phase immersion cooling tank at its Azure data center in Quincy, Washington. This marked the first publicly confirmed hyperscale production deployment of this technology. Following from 2023, from 2021 to 2022, Microsoft collected optional data under live workload. The company monitored system reliability, thermal stability, fluid behavior, and maintenance procedure. The object was to determine whether immersion cooling could operate safely and consistently in real-world cloud environment. From 2023 to present, the system continues to be evaluated for scalability. Microsoft is assessing whether the technology can support future high-density AI cluster and potentially enable deployment in a remote or edge location where traditional cooling system may be less practical. Although Microsoft has not announced full global rollout, the Quincy deployment server has a validated pilot that informs future infrastructure decisions. Overall, this timeline shows that the project evolved methodologically From industry precedent to internal research, the production activation, and finally to ongoing evaluation and scalability planning. Now, we establish when and how Microsoft deployed two-phase immersion cooling. Emmanuel will explain the business drivers that made this transition strategically necessary. Thank you.
Microsoft is one of the most financially disciplined company in the world. So when they fundamentally change how they code their servers, that decision doesn't just happen without serious reason. My name is Emmanuel Maduka, and my session answer the question, why did Microsoft invest in two-phase immersion cooling? The answer comes down to three converging business drivers. The first driver is a hard physical problem. For decades, chip makers made our processor faster by shrinking transistor, and smaller transistor meant less heat. The era is over. Transistors have hit a physical limit, so manufacturers now get performance by adding more cores and more power, which means drastically more heating per chips. Here is what that looks like in numbers. What conducts heat 26 times effectively than air. So water conducts heat 26 times more effectively than air. That's a verified engineering figure, not a marketing claim. The NVIDIA H100 GPU powering most AI training today has thermal design power for I think 700 watts in its server configuration. And AI workload rack now demands between 40 and 100 kilowatts of cooling capacity. Air cooling practically limits to 20 to 25 kilowatts per rack. The gap is not a minor engineering challenge, it's a fundamental mismatch. And Microsoft's own VP of data center development, Christina Ballard, said it plainly, air cooling is not enough. Moving to the next driver, driver number two. The second driver is commercial urgency. Microsoft has invested billions into OpenAI and integrated AI across its entire product ecosystem. Being as Azure Copilot, that commitment created a sustained, unprecedented demand for thermal intensive computing infrastructure. Look at this timeline. Before 2020, Azure scaled conventionally. Air cooling was adequate. By 2020 and 2021, AI workloads surged and thermal limits were hit. Then, in April of 2021, Microsoft activated their first two-phase immersion tank at their Quincy Washington data center. And this is the critical details. They ran real production workload through it, not a lab test. Microsoft team and Outlook users were being served by immersion cooled server. That tells you how urgently they need this to work. So moving on to the third driver. The third driver is institutional, and it's more about financial risks than environmental goodwill. Microsoft has formal investor disclosed commitments. Carbon negative by 2030, water positive by 2030 also, and removal of all historical emission by 2050. So these are timeline which Microsoft wants to meet, and it has included, it has helped drive their decision in moving into water cooling. These are not marketing pledge, they affect their cost of capital and their government contract eligibility. And traditionally, data center rely on evaporative cooling towers that consume millions of liters of fresh water daily. Two-phase immersion uses a closed-lid system, no direct water evaporation. And according to peer review research from Energy Informatics, Immersion cooling deliver a PUE of 1.02 to 1.04 compared to global average of 1.58. That's roughly a 50% reduction in total energy consumption for the same compute load. This number directly advanced Microsoft carbon targets.
So let's bring all this together. The three independent pressures, which is hardware constraints, AI marketing demand, and ESG obligations converge at the same moment. Here's the key insight. Each driver's alone was manageable. Together, they made doing nothing more expensive. Air cooling couldn't handle the heat. Conventional expansion couldn't meet AI demand fast enough. And incremental improvement couldn't satisfy normal sustainability. Two-phase immersion cooling solve all three simultaneously, which is exactly why Microsoft deployed it at production scale in 2021. Now I will hand over to my teammate Aaron, and he will explain how the technology actually works. Thank you.
Two-phase cooling, liquid cooling implementation is both technologically simple and advanced at the same time. The core concept is incredibly simple, and it is the simple application of heat to a liquid having better thermal conductivity than heat through air. We see this every day in practice when we boil a pot of water. Uh, In concerns of the unit, we're going to refer to it as a rack because it is essentially a heavily engineered server rack. In this case, this one rack can host 48 servers, so 48U rack, assuming for 1U servers. Uh, there is no specialized design required for the server computers, so they do not need to be specially engineered, and they do not need cold plates in order to function. Servers can be extracted manually by one or two technicians if needed during maintenance, allowing for quicker maintenance than having to wait for an entire tank to drain in order to service one machine. One to a few machines, we should say. The cycle of cooling is simple, simplicity at its finest, with some advanced caveats to it. The method of transmitting heat to the fluid is direct contact. The server rests within the fluid. When the fluid that is making contact with the chips on the motherboards uh, gets heated, it reaches 50 degrees Celsius, it boils, it converts to vapor, and that change in density allows the currently vaporized fluid to rise to the top, while the non vaporous fluid stays below to continue the cooling cycle. That heated vapor then proceeds to make contact with a condenser, and the heat is extracted through the condenser, which allows the coolant to rain back down on top of the vat, as it were, and that heat is then extracted externally through a simple conduction pipe. That pipe can be used in a dry air environment, as this piping would average be probably about that 50 degrees Celsius, maybe a bit lower. And that means it is going to be a or high temperature than the ambient air around it. And just by pure exposure, it will, in essence, end up radiating this heat.
My name is Jaswinder and I will be presenting the topics benefits and efficiency. The first major benefit is superior thermal performance. The servers are completely submerged in the special dielectric liquid. When the components heat up, the liquid actually boils carrying away the heats in the form of vapors, and servers run at the full power continuously without the thermal throttling. This is why Microsoft has selected this method, because it has a high performance workloads. The second part, the efficiency, is the major gain in the energy. It eliminates the servo fans and reduces the reliance on the air handlers like previously in the traditional methods uses a lot of power from the fans, air conditioning, and the cooling systems. So with the immersion cooling, most of the equipment that were previously needed are now not needed anymore. So it's a good way, and it's reported that 90% of reduction in the cooling energy consumption is noted. And also the third point I'm covering for the benefits are because it saves water and it maintains sustainability. Unlike the cooling systems like the previous use, it doesn't need any continuous water evaporation. The technology is used as a sealed and closed loop system. Vapors produced during the boiling are captured and returned to the liquid from the without losing the state of its water. And the fourth and most important point I have covered is it reduces the noise pollution and the mechanical failure by the removal of the several fans, servo fans, and reduces the noise pollution, the vibration. And because it is summer, servers are summers, they are no longer rely on the internal fans and air handling units. It eliminates the noise, and it leads to the longer hardware lifespan of the failure points.
Hi, so I will present the risks and challenges we face in immersion cooling. So one of the challenges is fluid handling and chemical risk. So one of the biggest risk in two-phase immersion cooling is the fluid itself. So Microsoft relied on 3M's Novak fluids, but then 3M announced that it is discontinuing all PFA based chemicals by 2025. So this creates a global supply shortage or chain gap with no direct replacement available. And so this is one of the challenges that Microsoft is facing with affected uh, their boiling performance and cooling efficiency. There is also material compatibility issues like standard PVC cables and some server components can crack or break down in the fluid, meaning only certain material like LSZH cabling are reliable. Another challenge they face is infrastructure and maintenance challenges. So, in this two-phase immersion, it requires specialized hardware, sealed tanks, and condenser system that traditional data center don't use. And so, most of the self servers are not immersion ready. So, Microsoft had to partner with certain vendors like Wing for custom equipments. From a maintenance standpoint, technician also needs to new training because working with boiling dielectric fluid is very different from air cooled racks, and task the and certain tasks like fluid testing, condenser checks, and tank sealing introduce new operational complexity. Uh, one more one more challenges they face is reliability and long-term operational risk. So two-phase immersion is still relatively new and there isn't enough multi-year data on how components behave after years of exposure to boiling fluid. There are also performance risks such as vapor bubble formation or film boiling, which can create hotspots and reduce cooling efficiency. In addition, immersion introduced new failure modes like vapor lock, seal failures, and unstable boiling under heavy workload. So another challenge is industry and ecosystem risks. So for this one, industry-wide readiness is still limited. Very few companies manufacture compatible fluids, tanks, or servers, so that the supply chain is still immature. There are also no universal standard for immersion server design, cabling, or maintenance progress. This increased vendor lock-in, meaning organization may be stuck with a single vendor, single supply for the fluid and hardware for a particular vendor. Since Microsoft is still one of the only large-scale adopters, ecosystem support and competition remain limited. Another challenge is environment and regulatory challenges. So there are growing environment concerns due to PFA regulation. Many current immersion fluid contain PFAs, which government are starting to restrict because they persist in the environment. This could lead to bans, disposal challenges, or forced phase out in the future. One of the next last and final challenges is deployment and location challenges. So in this one, deployment and location pose practical challenges. Immersion tanks filled with fluid are extremely heavy and require reinforced flooring and spill containment systems. If these systems are used in edge or remote sites such as micro data center at 5G towers, maintenance become more difficult due to limited access and fewer trained technicians. So this is all the challenges that we are facing right now with the immersion cooling. Thank you.